Hello everyone, welcome to my talk. My name is Weihao. I'm currently a postdoc at University of Washington. I'm going to talk about our work on optimal policy value estimation in contextual bandits. This is a joint work with Gregory, Valiant, and Brunskill. In this paper, we consider the optimal policy value estimation problem in the contextual bandit setting. To give a concrete example for the contextual bandit setting, consider the following music recommendation example. The following procedure repeats for many rounds. Each round, a user arrives, and the recommendation system chooses one of the albums to recommend to the user. Each user and each album has a feature vector which is available to the system to help decide which album to recommend. For example, the user's feature might include the user's age, location, and listening history. The album's feature might include the title, composer, and lyrics. Say in this case, the system recommends KK Disco to Mr. Nook. It turns out Mr. Nook does not like this album and gives a thumb down feedback. The system receives the user's feedback and this concludes the first round. In the second round, a new user Admiral arrives. Based on his feature, the system recommends the album Steep Hill. The Admiral likes the album and gives a thumb up feedback. The system receives this information and this ends the second round. This procedure will repeat for many rounds, and the recommendation system will keep improving its recommendation policy over the round and try to get as many positive feedbacks as possible. Ideally, after a certain number of rounds, the system is going to find a near optimal policy. The question we ask in this paper is it possible to estimate the performance of the optimal policy before we can find the optimal policy? Why do we care about this problem? Well, quickly learning the performance of the optimal policy provides vital information for humans to make scientific and business decisions. For example, in a medical setting, the researchers could stop the experiment early if they learn that no treatment policy can yield satisfactory results. The information about the performance of the optimal policies is also useful for model selection. In many applied scenarios, we need to choose between simple versus more complex models. If we only consider simple models, it takes fewer rounds to learn a near optimal policy in that model class, but the performance of the optimal policy might not be that great. If we also consider more complex models, it takes more rounds to learn a near optimal policy, but the performance of the optimal policy could be better. However, without knowing the performance gap between the optimal policy in a simple and complex model, it is impossible to decide which model to use. In the contextual bandit setting, it is up to humans to collect data and construct the feature for users and actions. There are many choices for what data to collect and what feature to construct. Data collection can be very expensive in some cases, so we don't want to collect lots of certain kind of data and then realize the optimal performance is insufficient. Let me describe the model assumption of this work. In this work, we assume there are k-arms associated with unknown coefficients beta 1 up to beta k, each with dimension d. For each round t, nature samples a context vector xt from a normal distribution with mean mu and covariance sigma. The learner sees the context vector xt and chooses an arm to pull based on that. The reward for pulling the eighth arm is beta A transpose xt plus independent noise. In this model, our goal is to quickly estimate the effective reward of the optimal policy. Here's our main result. Assuming that the covariance of the context distribution sigma is known, we propose a non-adaptive algorithm that estimates the effective reward of the optimal policy up to additive error epsilon in t equal to square root d times k times log square k over epsilon square round. For comparison, notice that learning any non-trivial policy, for example via linear UCB, requires at least t equal to dk rounds. We remarked that the known covariance assumption can be achieved by estimating the covariance through a large number of context vectors offline, which is often available in practice. Our algorithm also generalized to the unknown covariance setting. On the lower bound side, we show that no algorithm, including adaptive ones, can estimate the optimal reward with error epsilon in square root d times k over epsilon squared times log k factors. This implies that our algorithm is optimal up to log k factors. How does our algorithm work? Our algorithm relies on two observations. First, know that the expected reward of the optimum policy can be written as follows. For context X, the optimum policy should simply choose the arm that maximizes beta A transpose X. For simplicity, let's assume the covariance of X is identity. Then, this quantity, by definition, is the Gaussian width of the set of betas. It is not hard to see that the Gaussian width of the set of betas is completely determined by the pairwise correlation between betas, since Gaussian width is rotation invariant. Thus, all we need to estimate is the pairwise correlation between betas. Our second observation is that estimating the pairwise correlations is much easier than estimating beta itself. Since there are k d-dimensional vectors, it takes k times d rounds to estimate all the betas, while we give a procedure which estimates all the pairwise correlations in k times square root d rounds. We know that the Gaussian width is completely determined by the pairwise correlation between betas. However, how robust is this mapping when we have some error on the correlation estimate? We leverage a quantitative version of Solokhov-Furnish inequality due to Saurabh-Chatterjee, which implies that the gamma additive error on the correlation translates to square root gamma log k error in the Gaussian width. The square root gamma log k dependency is tight. Intuitively, this is because the coordinate-wise maximum of an isotropic Gaussian distribution is about sigma times square root log k, where sigma is the standard deviation. And we're going to have this error even in the simplest setting where beta are all orthogonal to each other and have the same norm. How do we estimate the correlation? We give a simple non-adaptive algorithm that efficiently estimates the correlation between betas. The algorithm just uniformly pulls each arm t over k times. For each arm A, we denote xai, yai as the context and reward we get when we pull the a's arm. For a pair of arms AA prime, our algorithm simply computes the average of the product of y times x for both arms. And we claim this is an unbiased estimator for beta A transpose beta A prime. The reason is the following. Observe that the expectation of yai xai is beta A, assuming the covariance of xai is identity. Since the same observation holds for arm A prime, the expectation of yai ya prime j xai transpose xa prime j is just beta A transpose beta A prime. And we show that as long as t is order k times square root d, this estimator can estimate all the correlations between betas accurately. We evaluate our algorithm on both synthetic data and real data. For synthetic data, we sample each context randomly from a standard normal distribution of different dimensions. There are 5 arms, and the unknown coefficient of the arms are also generated randomly. The x-axis is the sample size for each arm, and the total number of rounds is the sample size times 5. The y-axis is the estimated reward. The blue line is the true reward of the optimum policy. The yellow line with the arrow bar is the estimated reward by our algorithm. The red line is the performance of the learned policy with different sample sizes. From the plot, It's clear that our algorithm can estimate the optimal reward well before learning a good policy is possible. And the advantage of our algorithm is more and more obvious as the dimension grows. We also evaluate our algorithm on a simulated joke recommendation system on the gesture dataset. The gesture dataset is the joke rating dataset, which has 70,000 users rating of 100 jokes. Each round, the joke recommendation system will pick one of the 10 jokes to recommend to the user, and the goal of the system is to maximize the user's rating of the joke. We generate a 2,000-dimensional feature based on the user history. Again, the x-axis is the sample size for each arm, and the total number of rounds is this sample size times 10. The y-axis is the reward estimated. From the plot, we can see our algorithm outperforms learning-based algorithm by a large margin. I want to conclude my talk with future directions. One major restriction of our result is that the Gaussianity assumption. Although we have illustrated in the experiment section that our algorithm is not restricted to Gaussian data, it is theoretically possible to construct counterexamples to make our algorithm fail. It remains an interesting open problem whether our result can be generalized to other distributions. Our algorithm is unadaptive, and we show in the lower bound that adaptivity doesn't help in the worst case. However, having adaptivity might be necessary if we want instance optimal algorithm. Finally, our current algorithm gets data through pure random exploration. It is worth understanding whether similar approaches can be applied on top of existing Bandit algorithm, for example linear UCB, and still achieves good estimation guarantee. Thank you for your attention. Please refer to our paper for more details.